So let's recap. We've had a look at the theory of quantum mechanics as evidenced through the two-slit experiment, and we've had a look at the history of quantum mechanics. And to recap the theory, everything's a wave. An electron is a wave, a nucleus is a wave, a molecule's a wave, an atom's a wave, you're a wave, I'm a wave, the room is a wave. And waves aren't exactly what we thought they were. They do slightly strange things when you measure them. And this theory, although it does sound a little strange to begin with, turns out to explain to a dozen significant figures or more every property of everything we've ever measured. Okay, it has no known bugs. Now we saw, especially through the history, how it explained the existence of atoms and how they work. We saw how it explained absorption and emission, the photoelectric effect, interference, and so forth. But our history only went through to about the 1920s, where the modern form of quantum mechanics finally emerged. So what happened after that? So after that, the next major advance happened when we tried to marry the theories of relativity with quantum mechanics. Now not only did that help us get the details right, so that we could get a dozen digits of significant figure agreement between theory and experiment, it also actually put a lot of restrictions on our quantum mechanical theories. In order for our wave evolution to obey the principle of special relativity, there are only certain theories that would work. And it turns out that some of those theories actually predicted particles that we'd never seen before. And then we went and looked for those particles, they were there. And this was the first time that completely new things had been discovered from theory rather than from experiment first. The normal role of science was that things would be observed and then theories would be developed to explain those things, and then those theories would be tested by further experiments. In this case, the principles behind the theory suggested a slightly different version of the theory, and that version of the theory made predictions that turned out to be correct, and we saw completely new phenomena, in other words, entirely new particles in nature that we hadn't seen before. And it didn't stop there. Quantum field theory, which is what this theory is called when you marry relativity with quantum mechanics, has predicted many new particles which have been observed, and also new forces and relationships between those forces, all of which have been verified to the best of our ability. And our best model of all these particles and forces is called the Standard Model. And you can learn more about the Standard Model in an upcoming module. The next thing that improved over the last 100 years since quantum mechanics was first invented was our understanding of the Correspondence Principle. And the idea here is that the quantum world, where everything's a wave, somehow has to correspond to the world we're used to for very large things. So even if you start to accept the evidence that an electron is a wave and can go through two slits at the same time, the idea that we're made of electrons and things that can go through two slits at the same time, the logical conclusion of that is that we're a wave and that we could go through, say, two doors at the same time. And we kind of reject that idea because we've never experienced anything like that. And we now have a far better idea of exactly how quantum mechanical behavior can lead to things that look like classical behavior at large scales. In the early days of quantum mechanics, Bohr took the rather controversial view that the quantum world and the classical world were distinct. He viewed quantum mechanics described the world of microscopic things, so atoms and subatomic particles and things like that. But the classical world, where you have cats and trees and flowers, is a very different beast and was described differently. In other words, he didn't think that actually there was a continuous picture that you could go from one to the other. Now, a lot of people had trouble with that because it seemed like an artificial boundary. If you describe one atom with quantum mechanics and 10 to the 23 as classical mechanics, what do you do with 100,000 or a million or a billion? Like, there must be some kind of transition. And if our model changes so dramatically from one kind of description to the other, then that gives us a kind of problem at the boundary. And this is more of a problem these days because we're very deliberately engineering large quantum states. We're building quantum systems that have large numbers of particles or large spatial extent. And what that means is we really need to know how to describe them. And thus far, quantum mechanics has always worked. And so we've tried to resolve this conundrum of having two different pictures for small things and big things by trying to see how the description for small things can extend to the big things and look like the world that we're used to. This is particularly important when looking at the most confusing of the postulates of quantum mechanics, which is this mysterious wavefunction collapse, which is where the behavior of particles seems to depend on whether you're looking at them or not. It's where the wave is traveling along as a wave, it can go through multiple slits or whatever else it does, and then when you look at it, it suddenly jumps and the wave function changes. And even over the last couple of decades, we've had an improved understanding of exactly how a quantum system interacting with the things around it leads to this apparent wave function collapse. And the final big story of recent developments in quantum mechanics is that we're starting to really use the quantum properties of things in engineering. We're trying to build quantum devices that really use this wave-like nature to do things that you can't do with classical devices. So for many decades, we've needed to understand quantum mechanics in order to understand the properties of materials and things like that. But now we're using the stranger properties of quantum mechanics as fundamental parts of our design.
Hello, I'm still Kyle Hardman, and we're in the Quantum Sensors Lab at ANU. And in here is still the coldest place in Canberra, possibly Australia.
Hi, Kyle.
Hello, Joe.
Hi. It seems like there's a lot of effort going here to make these atoms really cold. Why do you do that?
Well, we go through all that effort so that the wavelength of the atoms become very, very large. We can then take the atoms and make them go through two separate paths and interfere them at the bottom. The interference pattern is strongly correlated to the acceleration of gravity, and because of that, we can make a precision measurement of the acceleration of gravity.
Right, so using quantum mechanics for good?
Using quantum mechanics for good.
Great.